Okay, so good morning, everyone. My name is Zwiener. You all have heard the talk on Friday, I guess. So I was not sure whether there will be a few more people who haven't seen my talk, so there will be a few videos you might have seen. But the core idea here for this lecture or workshop is to tell you in detail how the drone navigation works and how the drone navigation and the drone control works. So while on Friday was more general, I actually want to go into detail and show you the equations and how it really works on the inside. Although 90 minutes still is too short for this topic, so I have to generalize at a few edges, a few times, and a few sharp edges. But still, the idea is that it gives you the tools to actually develop your own UAV flight control. Yeah. So again, I will show you a few videos you all have seen already. Then I want to begin with multi-copter technology in general. Then multi-copter control, that means how to keep a multi-copter in the air, stable in the air. And then I want to go to the navigation part. The focus here is on inertial navigation in combination with GPS or GNSS in general. And then the last part is how to design a inertial navigation system combined with GNSS. With the focus on low-cost MEMS technology, so single frequency GPS receiver, low-cost inertial navigation sensors. So not the expensive things like L1, L2 receivers and 50,000 euro IMU, no, rather a 70 euro IMU and a 50 euro GNSS receiver. So that's for part 5. And so you've already seen that. I want to go a bit more into the technical details here. What we see here is a attitude stabilization only. That means the pilot has to manually set the throttle to stay in the air, and the pilot can set the roll and the angle. So he has to do the position hold on its own. So the aircraft here only stabilizes the angles. And you see, this can be a bit, it's hard to hold the height. And landing is also not so easy because you have to be very careful with the throttle. So if you just let the stick go, you would immediately crash down. Yeah, so that was that. And the same is true here. There is a ascending technologies attitude stabilization in there. So one experienced pilot from ascending technology still has to do the manual throttle. So if he would, in this situation, let go of the stick, 400 kilograms would crash down, and roughly 1 million euros would be gone. So also here, for the first flight, we only had attitude stabilization. So, and this is also true for here. I'm not sure if I showed that video on Friday. So this is earlier than the video before. So this was a 1-4, so it's 4 times smaller than the model you've seen in the video before. This was a test flight, also with 18 propellers to test it. And you see the power line. You've seen that UAV before, but this is a new video. But it's still the same. The pilot has to manually set the throttle. This is what you normally do on the first test. If you develop your UAV, you probably want to test the attitude stabilization first and do the manual throttle. And then if everything works, then you can enable altitude hold, and then you enable position hold, and then it's the easiest to fly. But the first step is to do the manual throttle. So you say, okay, roughly go with the stick to 50%, all motors spin up to 50%, and it flies. And the attitude stabilization is done by the control computer. And you see there are quite some vibrations on that. I will come to that later. But this can be a bit tricky to have those kind of vibrations. And here you see the same thing with position hold and altitude hold. You just don't have to care, and it's the most relaxing way to fly. But also, you really have to. You need an advanced flight control. But I will, in this talk, try to explain how this control algorithms, how they work. The same goes here. We've seen that before. And again, position hold. So in here, the navigation Kalman filter will be explained in chapter 5. That works here. So yeah, as I said, the idea is to give you the whole theory how to get to that navigation state here, and how to do the control. So that's the idea. I hope I can do that in 90 minutes. But that should be the result from the math behind this lecture. So enough of that. Again, you've seen that the Kalman filter from chapter 5 is, well, chapter 5 is a bit more simplified. But it basically is the core that you see here. So this is the Kalman filter from chapter 5, where you take inertial measurements and the GPS measurements, and you get this high relative accuracy. Yeah. So just to show you why these equations later on will be useful. Okay. So what are the basic elements of a UAV, of a multi-copter? We need motors, propellers. We need the so-called motor controllers, or electronic speed controllers. Often on the internet they're just abbreviated as ESCs. Some sort of frame to hold that all together. Battery, lots of batteries, or one big battery. A microcontroller, for example, that does all the calculations. So you need to run your own software algorithms on some microcontroller. With a real-time operating system, so you cannot just say, okay, I'll put a Windows PC on that. You need a real-time computer where you say, okay, in 2 milliseconds I need to do this or that, and in 10 milliseconds I need to do this or that, because timing really here is critical. You need to read the IMU at exactly this millisecond. You need to set the motors at exactly this millisecond. So if, for example, Windows is busy for 500 milliseconds, that won't work either. So you need a real-time operating system and a dedicated microcontroller. And of course you need all the sensors. Here in this lecture I assume we have an accelerometer, gyroscope, a magnetometer, some sort of GPS, GLONASS, GNSS receiver, and a barometer. The GNSS height is not so good. A barometer works really well. But if you use the pressure readings from a barometer, it's quite noisy, but it's more or less normal distributed. So you have actually a pretty stable height measurement that is, let's say, normal distributed with like 1 or 2 meter standard deviation. But that works really well in the Kalman filter with the IMU. So you have this normal distributed measurements from the barometer, fuse it with the INS, That gives you a really good height, better than the GPS height. Okay, so first for the motors. This is for smaller UAVs, for like the 5 kilogram or class brushless motor, brushless outrunner motor. They are pretty common. You see we've got 3 wires here, and I will, why that is, I'll come to in the next slides. So this is the motor, and the propeller just is strapped on here. So if you want to build your own UAV, you need at least like 4 or 6 or whatever you want to build, or 8, if you want to build an octocopter, 8 of those motors. And it normally is a good idea to not buy the absolute cheapest. They should at least be well balanced, so you don't get vibrations from a badly manufactured motor. So maybe spend €5 more per motor. Yes. But I don't want to endorse those products. There are many good motors. Important numbers for such a motor. You see the kV, the rounds per minute per volt. You see that actually here on the motor is 700. That tells you with how many RPMs the motor is spinning. Also, you need to check the supported voltage. So, for example, a motor says, okay, he can accept up to 4S. 4S means 1S is 3.7 volts, so you have to check, can the motor, does it support this voltage? The efficiency is quite important for a good flight time. And you also need to check the operating temperature. But we will come to that in a few slides, namely here. So, for example, if you say, okay, I want to use this motor, and you look at, and you will want to build your own UAV, you have to check the attributes of this motor a bit. So, if you, let's say, you want to have, you have a battery with 11.1 volt. 3S would that be? And then you can see, okay, 50% normally should be the throttle range where it hovers. You should aim for that. You see, okay, the efficiency with grams per watt that it lifts well, 5.7. But you see, this motor works better with 7 volts. So here it's more efficient. So this is something you need to consider. So you have to consider what input voltage you want, what propellers you have. You have here, this is 5-inch, 6-inch, 7-inch propellers. So this is the combination of all those components need to match if you really want to maximize the flight time. And you see, it can make quite a difference whether you are in this efficiency range or somewhere here. In general, higher input voltage is a bit more efficient, but the motor has to support it. So this motor has quite a high kV number, so for higher input voltages it will spin pretty fast. So the general idea is to go down with the kV number, so the motor spins more slowly, but go up with the voltage. So you have high voltage, but low currents that flow. That saves at the end, the battery runtime. So low kV numbers and higher voltage if you want to maximize the efficiency in general. But this here is a motor that's optimized for lower voltages, so you have the highest efficiency in this low voltage range. But depends on your application. If you want to build a very small, very agile UAV, you probably want to go for higher kV numbers. You have smaller batteries. If you want to build a larger, a hexacopter, octocopter that has to carry a heavy camera, then you go for lower kV numbers and higher input voltage. And also check the operating temperature, so you see, okay, here the motor gets a bit warm. Yeah,
How
so
it's about the sound, probably it's better to shift the RPMs to the older sound, as if how you shall lose the hearing.
yeah, well, they are also
9 kilohertz it's dramatic sound, but 20 kilohertz it's nothing.
normally, to be honest, I don't care about the sound. I care about
Oh,
the runtime,
okay.
but they are noisy in any way. So, for the motor controller, this is also important. The ESC. We've seen from the motor has three wires. So these three wires they go in here in the motor controller. These two wires they directly go to the battery. So you buy a normal battery, a rechargeable battery. And what you then do, you connect this this yellow line to your microcontroller and you give a signal how fast the motor should spin with this single line. I will show you in a few slides how this works. Again, motor goes here, the direct current goes here to the battery, like your 11.1 volts, for example, and you have a digital signal with your avionics how fast the motor should spin. And what we also see here, this is a motor controller that allows up to 400 Hz of update rates. If you build a 5 kilogram UAV, you should use a motor controller that supports at least 400 Hz. If you have older or cheaper motor controllers with 100 Hz, you won't get such a stable climb behavior. Other important attributes for a ESC, you should see if the current is okay, but normally this is not a problem. For smaller UAVs, they don't need such high currents. And again, I said you should more aim for higher voltage and lower currents anyway. Something that's also important is a linear thrust response. It also makes controlling easier. So a lot of motor controllers, they have a linear RPM response. But if you have a linear RPM, the thrust goes up exponentially, which makes controlling it a bit more difficult. So it's better if the thrust response is linear. So you say, if you go from 20% to 40%, you have a linear thrust response and not a linear RPM response. There is also a so-called PEC. And I go back to the slide. This is this line here. A lot of ESCs have that. You see the red line and the brown line. The motor controller gives you 5 volts. You can use that to power your avionics, your other parts, or you could add another battery. But it's normally quite convenient to just use the 5 volts that are provided here. And the weight of the ESC is also something that can be interesting because roughly for smaller UAVs you can say 1 gram equals 1 second of flight time. So if you can save 10 grams here and 10 grams here, it adds up. And you also need to check the input voltage of the ESC. Like, does it support 40.8 volts, or maybe you want to go in the 20 volts range? You need to check that. So normally those ESCs are controlled with so-called PWM, also with modulation signal. I'll just go back to the slides. I'm talking about this line. You connect this line to your microcontroller, and if you give such a signal, you say, okay, it's 0 volts, you go up to like 5 volts for 1 millisecond. The motor controller knows, oh, someone is there, and it will activate itself. This means 0% throttle. If you create a signal that is up for 1.5 milliseconds, then the motor controller will spin up the motor to 50% of throttle. And if your signal is on high for 2 milliseconds, it will spin at 100% throttle. This is how you control the motors. That's all to it. Normally, the microcontrollers have some dedicated hardware to help you with that, so it's not that hard to program, because this is quite a common task. And I said the ESC I showed you has 400 Hertz, so that means you can do that 400 times per second. 500 Hertz would be the max, because you have then it would be like directly following, each pulse would follow each other, it would be hard to distinguish. So 500 Hertz here is the max. Otherwise you need some other architecture to talk to the motor controller. But 400 Hertz normally is plenty. Okay, that's how you control each individual motor, PWM. Okay, so this is basically all we need. So we have the battery, we have the motors, we can control how fast they spin. And now we just need to think how to properly talk to the motor so that the UAV flies stable. Because just like saying, okay, we spin all the motors at 50% is not sufficient. And there is a handy tool, a handy website. It's called ePower. So if you say, okay, I want to build my own UAV in the 5 kilogram range, this website is tremendously useful. You say, you give this website, okay, I want to have this battery, 5,000 milliampere hours battery. I have a 30 amps motor controller. You say, I want to use this motor, and then this website will calculate the basic parameters of your configuration. Now, of course, you have to supply the weight. For example, here I have a hexacopter, six motors. I say my total weight should be 2.5 kilograms. And that website here, for example, calculates we have a hover flight time of 40 minutes in that configuration. We have a flight time of 5.5 minutes. The difference is in hover flight, you can stay up for a much longer time. If you really fly maneuvers, your flight time goes down, as you can see here, from 40 minutes to 5 minutes. And they also calculate some mixed flight time, so maybe this is the most realistic flight time. If you buy commercial drones, they probably give you the hover flight time. You also see the max speed here for this configuration is roughly 50 kilometers per hour. We see we have, in this configuration, we have 1.4 kilograms of payload free, so we can attach a heavy camera or some other sensors that we need. If we go down with the total weight, this would increase the hover flight time into the 20-25 minutes range. So you can play around with that. You say, okay, I want to build that UAV, I want to carry this or that, and this tool gives you quite a good estimation what your UAV can do. And it will also calculate if, for example, your motor gets too hot, if you have here the efficiency, if you have a bad efficiency combination. So, quite useful. Yeah. One last word to efficiency. You see here from a specific motor, the efficiency curve. This is the curve here, efficiency. The motors need to spin at a certain level to really be efficient. So this is something you need to consider when you design your UAV. Again, if you use this website, it will tell you that, but you want to spin the motors at 50% to really have the efficiency of the motor and to achieve good flight times. Some relationships for multicopters. So if you have larger propellers, you get longer flight times, longer hovering flight times. But you have this additional mass of the propeller, so it takes a bit of time to change the RPMs. So you lose a bit of agility here. So if you want to have a very speedy UAV, you don't want larger propellers, but if you want to do some photography, photogrammetry, you probably want larger propellers. And carbon propellers, they are also more efficient. So if you have, for example, 20 minutes flight time with normal plastic cheap propellers, you get like 22 minutes from carbon propellers. Again, for photogrammetry, interesting, 10% roughly more flight time, but they're really dangerous. So if you develop your own flight control, I would strongly advise you not to use carbon propellers because they really can cut your finger. So they're really dangerous. For experiments, stick to plastic propellers. They just break, and you replace them for €2. Another thing is the carbon propellers are quite expensive, so you have to pay like 20 euros or more, and the plastic propellers are 1 or 2 euros. I already said that. Increase the battery voltage. It's also a way to increase efficiency. So you choose high battery voltage and you choose motors with lower kV numbers. The problem is, the higher the battery voltage, the more weight you get from the battery. So this is some trade-off. And again, this eCalc tool, this website I've shown you, is quite handy to see if it balances itself out, if it actually is useful. And also, the battery, they get more expensive, so you have to pay for a 6S battery like 120 euros, a 4S battery is 70 euros. If you go up with the battery voltage, you need more expensive ESCs, so you have to pay for this additional flight time. Okay. So far that was what do you need to consider, what components you need to buy for your UAV. And so let's assume now we have a UAV that has all the components. Now how do we control the motors to keep it stable in the air? And the only way to control it, we control the individual motor throttle. And this is something a human cannot do. If we think about the 18 propellers multicopter you've seen at the beginning, you cannot individually control the single 18 propellers. And even four motors would be quite hard to control. So we need to develop algorithms for that. We need the current navigation state and the desired navigation state. For example, we have this angle, but we want this angle. The pilot, for example, says, I want to look forward, or the pilot says, I want to lean to the right. So we need to go from the current navigation state to the desired navigation state. Or this is not even controlled by the pilot, but by a trajectory that you've defined, that you say, okay, the UAV should fly around some ground area, and the desired navigation state is calculated by your waypoints, for example. In my slides here, I use a quadrocopter, for example, because 18 motors would be just confusing here, I guess. So what we can do, we control the single the single motor throttle. And you always need 50% of left spinning motors, and the other half need to spin, well, clockwise and counterclockwise. Otherwise, you create some torque around the z-axis and it just will be hard to control. So zero torque on the z-axis is what you want. So a even number of motors is beneficial here. Otherwise, you need to do that in software and say, okay, I need to create a zero torque in the software. So it's easier if you have an even number of motors. And that's the first thing. If we, for example, for the clockwise spinning motors, if we reduce here the throttle and increase the throttle on the other motors, then we create a torque on the z-axis, so we can change the yaw angle. We change our direction just by changing its throttle here. So if we want to go up or down, we just increase the overall throttle. 20% on all, and we go down. 70% on all motors, we go up. And the roll and pitch angle, they are, for example, if we want to change our attitude here, we increase the throttle here, decrease it here, and it stays the same here, and then we make that movement. So these are the parameters that we can set. If you have a hexacopter, you need to do the same, but you need to distribute it. Or if you have a 18 motor configuration, you still need to do the same. You have to distribute the motor powers in such a way that you create this total torque, and then the aircraft will change its attitude. Yes. Normally, if you're in the air, you use such a coordinate system. X is the roll axis where you're looking at. Y to your right, the pitch axis, and Z points down to the earth. If you have a ground vehicle, then Z normally points out. But if we are in the air, this is the normal northeast down coordinate system. So the first control loop, the attitude control loop, because it's the most important to keep the aircraft stable in the air. And it normally goes something like this. You have plant here means we have the motor throttle between 0 and 100%. And let's focus on the inner loop now. We have a desired rotation rate, and we have a current rotation rate. The rotation rate we get from the navigation, and we see that in the later slides. And we have a desired rate. Here, this is ideally an adaptive controller that sees that okay, we're spinning too fast and we need to slow down a bit, and dynamically adjust itself. For example, if you add a weight to the copter, it can adjust itself. But if you want to develop a very simple flight controller, a normal PID controller also works, where you just say, for example, we have a roll rate, how fast we're rolling, so the roll current, and we have a roll desired. We build the difference, so we have an error in roll rate, and then we multiply that by some number, so that would be the key part, some number, and we directly send that to the motors, like we say base throttle would be 50% plus this number, and this would, for example, give us 55%. We do that for each axis, roll, pitch, yaw. But that would be a simple PID controller, but that is enough to keep the aircraft stable in the air. An adaptive controller is harder to program, but most of the projects just use a simple PID controller. They just take the difference between the desired state and the current state, multiply it by a constant, and send that to the motors. It's actually quite simple. The only thing is you need to find the constant that you need to scale. So this is a bit of tuning. So this actually is the point where you, a small UAV, you just take into the hand. It's quite dangerous, but you spin it and tune the number until it feels right. So that sounds a bit trial and error, and it is, but this is what you normally do in the simple case. Again, it's better to have an adaptive controller that itself understands how the motors should be controlled. But this is a topic on its own, adaptive control. But again, with a simple PID controller, very simple math, you just take the arrow, multiply it. You can perfectly control a UAV as long as the mass distribution does not change. So if you add a camera, you might need to fine tune these values a bit. This is the most critical loop, so that you have the rotation rates under control. And then you normally have a controller on top of that controls the attitude. So for example, if the actual roll angle is wrong, this attitude loop says, okay, we have a wrong roll angle of 10 degrees, so we want to have a desired roll rate of 10 degrees per second or something like that. So this is this cascaded attitude loop. If you develop that in C, this is pretty short. You just build the differences, multiply it, send it to the inner control loop difference, multiply, and then send that directly to the motor. So that is a few dozen lines of code, very, very simple. Again, adaptive control is a bit more complex, but that is the essential part to control the multicopter, to keep the attitude stable. And it's also the most complex control loop. Altitude control is a bit simpler, depending on your setting, but it's just the altitude is okay. We have this height, but we want to go to another height, so we increase the base throttle. It's again, we build the difference, multiply it by some constants, and send that to the motors. And that works quite well. So it's controlling the altitude is then pretty simple. You can, for altitude control, also create a cascaded loop that is similar to that. So the inner loop controls the velocity, the height velocity, and the outer loop controls the absolute height. This is also possible. This gives you the advantage that you can control the up and down velocity, which sometimes, for example, for auto landing, it's useful if you say, I want to land with 20 centimeters per second or something like that. But for the altitude control, also a single loop is sufficient. If you have attitude control and altitude control, the multicopter is already pretty stable in the air, but it will slowly drift away. So what you want is a velocity control. And the velocity control is pretty simple because it just sets the desired attitude. So not the pilot sets the attitude. The velocity control says, okay, I want to have a roll angle, or I want to have a pitch angle to move in that direction. Because if you change the roll angle, then the UAV will move forward. And if you change the pitch angle, the UAV will move to the side. So the velocity control then can change the position of the aircraft on the horizontal plane. But velocity alone is still not good enough in the long run. If you want to hold the position, you need an absolute position control that checks, oh, okay, we've moved too far away from that position, and then the position control will change the velocity, and as I said, the velocity will change the attitude. But what I'm trying to say here is once you have the attitude control loop, position hold is quite easy because it will just change the angle to stabilize it. So it really is that simple where you say, okay, I'm 2 meters away from my desired position, so I change my roll angle by 5 degrees and my pitch angle by some degrees, and we will move into that direction. Then the smaller the arrow gets, the smaller the angles get, and so you converge to that position. A bit simplified everything, but it actually is not that complicated to really control the 3D position of the UAV. So all in all, you have maybe, well, yeah, 400 lines of code or something like that. Just build differences, send that to the motor, and then your multi-copter will stay stable. So that is not so hard. Navigation is a bit more of a problem. Now I see, should we do a small break here? Yeah, 45 minutes, so make like 5 minutes. So break, I think there's coffee there. And if you have questions,
I have a feeling that you jumped over a propeller calculation methods. Just, I think every motor must be facet, specific propeller size and even propeller pitch and so on.
That's true.
That's quite tricky calculation over that.
That is a topic on its own, yeah.
Okay.
I have this slide where okay, there's the propeller, the diameter and the pitch. So this is what I was trying to tell here. Okay, you have to see. Okay, this propeller works on this pitch. This propeller is quite efficient compared to the small. You have to individually see.
Quite good certainty. Okay, but why you said that carbon propeller is dangerous? Can it explode, or what can happen about it?
For smaller ones, you maybe fleet, or for example, if you've seen the when you so
if you are coming inside.
Yeah.
Exactly.
And with plastic propeller, you probably will keep it finished. So, especially if you develop your attitude control, maybe you have a small buck. Maybe you touch the aircraft because of your own mistake. So in this stage, I would prefer.
In one of the first pictures, I think that this pilot is sitting in the plane of propellers, and I seen it very good.
Yeah, that was.
Just I know how many people was dying when this fashion for snow vehicle was coming.
That was actually.
That was such propeller with some 50 kilowatts.
That was not the most responsible thing to do, but they were the first, so they had to take some risk. But that's true, that's actually quite dangerous to stay in the plane of we can talk about email. Hello.
Viņam pagūst.
I guess so to do something with the alignment.
Yeah, this is over. The bugs station and all.
Jau piedomāju par to, ka vajadzētu iet
So
lejā.
we will likely not be around today, but promise me to be here tomorrow again.
Teicais karstais. Tur arī ir karsts. Lielajā bundulī ir karsts. Nu ko, taisam helikopteru.
Immediately the kind of deal from. So it's well, it would be slightly better, but because the second circle is around here, it's a bit the scale is a bit on the center. So they are the strongest position. Look at the PMT, okay, this is very good to make a picture, but where's the losses? Maybe we'll still go, let's see.
Is he alone here, or is he there alone, or has he some help?
Vai dar lektor, tutaj piję kawę i oferę tutaj.
Es vakar kaut kāds apskatījos. Principā man tāda saprašana, pie tās nezinu pakāpes, kāda man valda galvā. Šobrīd es būtu mieru, ja apvērām nezinu. Manuprāt, tur nekāda. Principā tie 4 spoguļi, mums kompensē aizskavas līniju visu.
Tu jau posties projām?
Es no rītā, tad jāuzstāšos ir gaisā rezonanses starp 2 spoguļiem.
Vismaz jāidu, kā redz.
Būs viegli garums.
Jā, es domāju, rīt plāns, kas
Nu, pieņemsim, mums ir uz 200.
šodien.
Tas par 0,2 mikrometri apkustīt kaut kādu mikrometru. Vecais 3 mikrometri.
Kaut kāds pamats kā.
Kādā nozīmē
Paldies.
Viena līnija iet caur elimināro kristālu, otra līnija iet pa gaisu.
decembrī
Bet nu labi, tu vari pats.
Vai tas tik ļoti cienīgi, jā, jo tas ir Ziemassvētku otrā diena. 19. gada.
Laimīgā kārtā tam pikosekundniekam jauns ir pietiekami liela.
Nu, žurnāliem ir vienkārši atver žurnālu čupā un FLD, esot kaut kādas klādes vai ne, klādes mums ar bērniem kastas izpurināja. Ir kaut kāds lentes vēl, bet...
Bērniņos izrunā, bet vispār vai tie žurnāli nav bibliotekā?
Nē.
Nē, nu, viņš, piemēram, esam visi kādēļ to bibliotekā.
Kādi, jā, kaut gan daži, teiksim, par laimi ir arī stacijā, jā, par apskatnieku vietu, var noskanēt un zinu, kā izskatīt.
Mazums iedās.
Arī filmiņu rullējuši ir 35 mm. Veseli kastatievi, bet tie ir praktiski nelietojami.
Cik nav tik laiknieki, jā. Mums kaut kur skatījās, tev apstīt,
Es manuprāt, tur ir tā, ja mēs paskaidām straisām, tad ir, tad būs, pēc tam jau būs daudz grūtāk. Tās sievietes cietums arktos un tā reizes nebūtu.
Okay, so if you don't mind, I will continue. I was running away a bit. So I hope I can compress that in the last half hour. Maybe I need to hurry up. Okay, so I've shown you the actually quite simple control algorithms for the position hold, attitude hold. To do that, we actually need attitude, heading, position, and velocity. So I want to show you how to develop such an inertial navigation system that gives us, or an integrated navigation system that gives us all these desired informations. Normally we have GNSS, IMU, so these are the core components, and this is also what we will use now. Additionally, we have a magnetometer to calculate where is north. Why we need a magnetometer, I will show you in the later slides. Barometer, because it helps to stabilize the height. It's better than the GNSS height. And this is, I would say, optional. So this is the line which pretty much every UAV flight control has. Here, optical system, some indoor drones, like the Parrot AR drone, they use an optical system to stabilize their position. And distance measurements to the ground to have a even better altitude hold. So this is something you can incorporate, but I want to focus on the core components here. Quite common is a single frequency, well, most of the time a reflex receiver, just because they have not only a good precision, but they give you a very good velocity estimation. And sometimes you can also access the raw data, so you can do some more advanced stuff like do baseline processing, things like that. But Weblog is pretty common, but again, this should be no
But why
advertisement.
using a single frequency? Normally every machinery uses 12 frequencies, 36 frequencies and so on.
No.
Or that's not a
No,
subtle number?
this is a misconception.
No, not the satellite number. Yes, it's just they still can track like 50 satellites at once, but they only have the L1 frequency. So we have single point positioning. You could also use L1, L2 baseline processing to give you a centimeter precision, but then you need to set up a base station and all that. If you can't do that, it's good. But normally people just want to place the drone on the ground and fly up, and don't want to set up a base station. But again, no, this should be no advertisement for that, but they are pretty good and they're pretty common. And the latest, right now I'm building a new flight control board with the MUBLOX 8. Very stable position here after 15 minutes, still very good. And more important, what you don't see here is the velocity is really good. You have centimeter per second accuracy for the velocity. So the velocity really is good, and you need that for the precision hold. But it's even more important than the position itself that you have a good velocity information, and you get that from the MUBLOX. And with the MUBLOX 6th generation, if you go near to a building, you have multipass and all that, and the velocity information gets quite bad. But with the MUBLOX 8 and the additional bonus satellites, you even have, if you fly close to a building, you still get a very good velocity vector. And that really adds to the security. So if you fly near the building, you can still navigate safely. So the more satellites you have, the better for the velocity. So if you build a UAV flight control, use GPS and GLONASS, and ideally Galileo would help here even more.
And what's about RTK and Zappos?
Possibly, yes. You can do that. You need the position and the velocity and the covariance matrix. And if that position is from a baseline, that's very good. Even better. But again, normally you just have you have a low-cost receiver, and people don't know how to set up a RTK base station, all that. But if you have that equipment, even better. Then you basically have one. If you have an RTK, centimeter precision, all is golden, and everything is good. The challenge is to use the cheap receivers and still achieve a good precision hold with what L1 only can do.
Oh, and what means a Kalman filter?
I'm not talking about the Kalman filter I will present later on. I talk about the MUBLOX internal Kalman filter. So if you have the MUBLOX, you can say, oh, I'm a pedestrian, I'm stationary, or I'm an aircraft. Or you can say the MUBLOX it's on a boat.
Yeah.
Once instead of aircraft 1G, I set the MUBLOX to the boat mode, so it thought it's just on the sea, and the height was not changing, and I spent many hours, why is the height not correctly detected by the MUBLOX? And then I found out, oh, okay, I have not set the aircraft mode, but the MUBLOX boat mode, and it just gave me always the same height. Anyway, their internal, if you see, you sometimes see such deviation plots, and they are set to pedestrian, and it looks even better, so you have like 10 centimeters of variation. But we need the aircraft mode because it allows up to 1G of accelerations and things, and then it doesn't look that impressive anymore. But so the MUBLOX internal filter is very important. It would be even better if you do your own processing, if you use the raw data and calculate the raw position with your own algorithms, and you have to complete through covariance matrix. But it's normally easier to use the MUBLOX position, but then you have to set the MUBLOX internal Kalman filter correctly. Yeah, this is, I said we focus now on the accelerometer and the gyroscope, but I will also talk about magnetometer and barometer when I talk about the Kalman filter design that we do. Historically, we had those on such a gimbal platform where it stays at the same orientation. And if you really want the highest precision, this is still the way to go, even after all those years. But this is not affordable for us here on multi-couples, and B, it's too heavy, and it just doesn't really work. What we actually use is here we use the MEMS strap-down platform. This is, for example, a sensor that you've seen working in the videos. The beginning is exactly this sensor. The sensor is pretty good because it's vibration tolerant. So other sensors, like for example, Bosch makes pretty good sensors. They are in the current smartphones, but they are a bit vibration sensitive. And this InventSense is quite tolerant to vibrations. This is important on a UAV. And so we have these structures. again, a bit, we're talking about MEMS. You see here, this is the MEMS area. If you go into, like there are fiber optic gyros, they are better. They can, for example, sense the Earth rotation rate. Ring laser gyros are even better. They have a much higher bias stability. And the best area is this, the mechanical systems. They're quite stable for their scale factor and bias stability. So for example, with such a sensor, you cannot really sense the Earth's rotation rate because the bias stability is so bad, it will just go away. So you cannot do something like initial alignment with the Earth rotation rate with cheap MEMS sensors here. You need to go into the fiber optic gyro area. But again, they get too large and too heavy for smaller UAVs. Anyway, I stick to the MEMS part here, but just to give you an overview that this is not the only system that you can use. And if you look at what gyroscope you need to put on a UAV, you can just use the MPU from InventSense that I've shown you, and it's all good. But if you want to choose another gyroscope, the ARW, the angle random walk, is important. But there is another slide coming. For more details, the bias offset is normally not a problem. You can just calibrate it. The only problem is it will change all the time. So we need later on our Kalman filter to estimate that bias offset. Another important aspect is the instability. So how quickly will the bias change? So because our Kalman filter needs some time to estimate the bias offset. So a bias stability is a very good property of a gyroscope. The bias itself you can estimate pretty easily, but if it's changing all the time, we have a hard time tracking the offset. Temperature sensitivity is also important. If you go from the UAV, you go calibrate it inside, or you go outside, you have like 10, 15 degrees Celsius temperature change, and the bias changes rapidly. That's bad. Vibration sensitivity is especially important for UAVs because you really have those high and strong vibrations. So you need a gyroscope that is tolerant to vibrations. It can behave really nice if you play around in your hand. If it's on the UAV, there are vibrations and it will drift away. That won't help you much. So these are some key aspects to look for. And for the angle random walk, this is what you often see in the data sheets. What does that mean? A angle random walk of 0.003 degrees per square root hours. What does that mean? If we multiply the square root of a certain time with the ARW, this gives us the 1 sigma error after 1 minute. So if you take that gyroscope and just integrate the rotation rates for 1 minute, your angle accuracy is probably that. So 160 because 1 minute, 1 divided by 60, and you take the square root. So that gives you an idea how good the gyroscope is. And you see that number in most of the data sheets, so that's important. Yeah, let's not calculate that. I just give you the solution here. So after 6 minutes, you would 6 minutes would be 0.1, the square root. So we have 0.01 degree of accuracy after 6 minutes. This is actually quite a good gyroscope. So probably not a MEMS gyroscope. Yeah. So much for the gyroscope performance. Now, coordinate system, probably already known, but I talk about the E frame or the ECF frame because this is where we get our GPS measurements. I frame, I mean the inertial frame, because our sensors measure relative to inertial space, so that is important. I talk about the navigation frame, northeast down, which is basically a geodetic system, but set is pointing down, and it's a right-handed system, which is good. And body frame is the coordinate system of the aircraft, and the sensor frame is the sensor coordinate system. And in the following slides, I will just assume that the sensor is perfectly aligned to the body. But if that would be not the case, you would have to translate. If your sensor is orientated in some whatever position, you would have to rotate it. So I will assume that all the sensors are in the body frame of the aircraft. And the aircraft body frame, no, there's first this one. Okay, so of course ECF coordinates, and we have the local navigation coordinate system depending on our position. So this is actually a local geodetic system. The end frame, the navigation frame set actually points down. Yes. Wait a second, where's the, maybe I jumped a few slides before. So this is our body coordinate system, X here, the roll axis, pitch to the side, and set the heading, the yaw angle. Okay, so let me jump back. I use the following notation. So if I want to rotate from system A to B, that would be the rotation matrix, some system A to some system B. Of course, you can combine that. If you want A to B, it could also be A to C and then C to B. And the thing is that you can B to A, but you want A to B, you can just transpose it. Quite useful because the microcontrollers have no real computing power. And if you, for example, want to have this rotation matrix N to the E frame, the standard geodetic knowledge in latitude, longitude, you can calculate those matrices. No big deal here. I'll show you that slide. The notation for the rotation rate is important because this is what we will use in the following slide. I'm not sure if everyone is familiar with that. So, if we have a rotation rate from a gyroscope, for example, or the Earth rotation rate, that means this is the rotation rate of system B relative to system A in the coordinate system C. So that describes, for example, how the Earth rotates in relation to the inertial system. But this rotation you can express in many different coordinate systems. So if I set up a local system here, or the ECF, it's different. But that means this is the coordinate system it's projected. So for example, yeah, well, it's still some arbitrary. This would be the rotation rate of a body with respect to the Earth. So how quickly does our body rotate with respect to the Earth, coordinated in the body frame? A good thing is if they are vectors, 3D vectors. If they are in the same coordinate system here, then we can add them together. So this here is B with respect to the inertial system. We can add that to B to I and I to E. We can add that. So we can prove those rotation rates. This will be important later on when we design our strapped-down inertial navigation system. 50 minutes left. Okay. One thing we will also need is the cross product can be expressed as a matrix. So when you see this notation here, this just means A cross B in matrix form. So, rotation rates. Just to remind you, we need to deal with the gyroscope rotation rates, we need to deal with the accelerations. So, what I want to express here is that if we use roll pitch yaw and we use the differential equations, the idea is then that we integrate the rotation rates to get angles. So we look at how quickly we are rotating, we integrate that to keep track of our attitude. If we use Euler angles, You see a problem here if this pitch, gets to 90 degrees, plus minus 90 degrees, we have here a problem and here a problem. That's why Euler angles are not the best choice here. It would work if we avoid those angles, but you can never be sure that your aircraft won't get pitch 90 degrees. This can happen. So then you divide by 0. No, that's bad. Also, there is this ambiguity at, for example, pitch 90 degrees. Is it now a roll angle, or do we change the heading? So this is the ambiguity here. Yeah, so that's why we use, or I would advise to use quaternions. Now I could talk for quite some time about quaternions. The important thing for us is that we can represent a rotation as quaternion. So if we have a quaternion with its 4 components, we can convert that into a rotation matrix. And if you need a complete or quick overview of all the equations, how to transform from this to that, from Euler to quaternion, quaternion to Euler, back and forth, there is a good tip for that. But I will spare you all these equations. But the reason why we use here quaternions is the problems with the differential equations that we have here with Euler angles. Otherwise, Euler angles are not bad. They exactly represent the orientation. So they are not pure evil, but they're especially good if you have your orientation for quaternions and you want to tell the pilot. The pilot has a hard time interpreting those 4 components, but roll pitch yaw is much easier to read and to interpret. So, before we go to the Kalman filter, I want to explain the strap-down algorithm. The strap-down algorithm. Strap-down because we have the sensors strapped down to the body in a rigid way. It's not moving. We get rotation rates from the gyroscope, and we get accelerations from the accelerometer. The gyroscope gives us the rotation from the body with respect to the inertial system in the sensor body frame. So, we, for example, need to subtract the Earth rotation because the gyroscope will also sense the Earth rotation. And the accelerometer will also measure gravitation, centrifugal force, Coriolis if we are moving, it's also sensed by the accelerometer. So we need to subtract those things and integrate it once. Rotation rate integrated once gives us a quaternion or a rotation matrix, depending on what equations we like here. Accelerations integrated once gives us velocity, and the velocity we directly need for the Coriolis correction. And if we integrate it again, we get the position. So for the strap-down algorithm, we need a known starting orientation and a known starting position, and also a known starting velocity, ideally 0 if you start from the ground. And that is the reason why we later on need to fuse it with GPS, because this will drift away after for each iteration step. For Coriolis, I will skip here because I'm running out of time. You need to be careful about gravity. We need to subtract gravity. So you have to consider, is my model giving me gravity or gravitation? So do I need to add centrifugal or not? You might have a simple ellipsoidal model, or you might have a complete real geoid gravitation model. But you need to be sure that you know the difference here. So what we just need to do is to integrate that. For accelerations to velocity and velocity to position is not so hard. To integrate quaternions, you can use this equation. Again, literature explains that all around. What we have here is we have the current orientation, and here we have the rotation rate, body with respect to Earth. And we have to be careful. This is what the gyroscope gives us, body related to with respect to inertial. So we need to subtract the Earth rotation rate, and this is how we do that. The Earth rotation rate to the inertial system, we rotate that into the body system and subtract it. So we have the pure body rotation, and then we can integrate that. For the accelerometer, this is what the accelerometer gives us. And this is what we actually want. We need to subtract gravity from whatever model you have. In the simplest case, you just subtract 9.81 or something, but would be the simplest case. The better you model, well, the better. So again, this is what we have from the accelerometer. We subtract Coriolis, just use this equation. We have the current velocity. We have here the Earth rotation, which is just roughly 15 degrees per hour. Of course, you need to add the correct value. The closer to the truth, the better. For my algorithms, I just use the definitions from the WGS84 ellipsoidal model. Yeah, so this is basically all you need to integrate. You read your accelerometer. Coriolis gravity gives us the change in velocity. So we have now the updated velocity, and with the velocity we can update the position. So that's all. One problem is this part here. When I say you just integrate it, it actually means during a small time step, for example, we have 100 Hertz, we have 10 milliseconds where we're still rotating. So we need to integrate something that's constantly rotating. The accelerations are constantly rotating, and that is not so easy to solve. Here, this is what you would need to solve. But there is a good approximation from, you can find that in Pitterton. You just take the accelerations then, multiplied by dt, and you're done. You take the last known orientation matrix, and you add that correction term, which gives you a very good approximation of this here. You can skip that altogether. You just take the acceleration and multiply it by dt. That also works, but if you want to have a really high precision inertial navigation system, you need to really consider that it's constantly rotating, and you need to add this term. But again, the first approach would just be take the accelerations multiplied by dt and use that. But you will, for example, the simple approach you get after a few minutes 50 meters of error. If you use the correction, you have like 1 meter of error. So you see there is quite a significant error introduced by ignoring that term. Okay, so, but if you implement something, just get, for example, Pitterton, they have all the equations written down there. For the other integration, you can just take the velocity, multiply it by dt, use Euler. It works. Just you always add some small error, so maybe at least use Simpson or a holistic integrator, or during my study times I heard the lectures from Jan Wendel at the KIT. He recommended just using Kuta fourth order for all these differential equations and use that for integration. But you can already with those you get pretty far, especially with MEMS. With MEMS sensors you can like stop here or something like that. It's good enough for those cheap sensors. Something I also want to show you here is how this is with perfectly fine data at 100 Hertz. If I just integrate that, you see here the 3D error after 1 hour, I get 9 meter of error. This was with the ballistic integrator, so that means I use this for integration. So if I just have a perfectly good IMU integrate that for 1 hour, I will drift away for 1 meter. A real world INS after 1 hour will have 1,800 meters of error after 1 hour. This is what you maybe have in a ship, a very good inertial navigation system in a ship. With MEMS, with cheap MEMS sensors, like we have on the UAV, you have an error of like 1 or 2 meters after 1 second or something like that. So you, after 500 or 800 milliseconds, your precision will go away. So, and the real world INS is like 100,000 euros, and really heavy, more like a mechanical system. So, yeah, even under best conditions, it will drift away. One thing I also want to show you, I've split it up in 2D horizontal error. This is this line, and the height channel. You see the height channel exponentially goes away, but the 2D error goes down. Why is that? After 2,500 seconds roughly, and that is so-called Zwiener oscillation. If we diverge from the true position, we use a wrong gravity vector. But the good thing is that this will artificially add an acceleration back to the true position. So this is actually a beneficial effect. We go away, we use the wrong gravity vector, but this will pull us back into the right position. Still, you get quite large position errors, but you see that the 2D channel is sort of stabilized while the height goes away exponentially. There's nothing that stabilizes the height in an INS. Anyway, yeah, Zwiener oscillation, 2,500 seconds of period. Yeah. So now I will use the remaining few minutes. Maybe you give me 1 or maybe 5 minutes more before we started later. I just want to wrap it up. So we have this inertial stretch-down navigation that will diverge, and we want to fuse it with GPS. So we could say, okay, from the INS at the beginning, if this is the probability, the density function, it's quite good, and after some time, we're unsure about our navigation state. So, for example, after 1 hour, we are very unsure. So we take, for the Kalman filter, our current state estimation. We take a measurement here in red, and we fuse it to in a optimal way and say, okay, this stabilizes our position. So this is what we do. We continuously integrate the INS with the strap-down algorithm. We keep track of the errors that are introduced by the INS. So this will make our prediction worse and worse and worse. And we take some measurements from the GPS with some known probability function and fuse that in the Kalman filter. So, Kalman filter, I probably leave the equations as they are. The important thing is we have the navigation state, which I will show you in a few later slides. We have measurements. Here the L vector, this would be, for example, a GPS position XYZ, velocity vector XYZ. We need a covariance matrix from those measurements. And we need some relation to the navigation state. For example, for GPS, it's quite easy. Measured position in the L vector, and the position is also in state vector, so our design matrix is just a identity matrix. Pretty simple. And then we use the well-known Kalman equations to make the fusion. Okay, so Kalman filter. And what we also need, we need to have a system model. So we have our state right now, and how does the INS, well, how does the position, how are the errors, how do they behave? So this is what we need to have in the H matrix. This is what we need to find. How does the errors from the INS influence our position, velocity, and so on? So the most important thing right now is find a good H matrix. The good design matrix is not so hard. As I said, it's just the identity matrix. So Kalman filters equations are well known. The design matrix A here is no problem. So what we need to find now is the system model. How does the system behave? How can we make predictions? I want to show you a error state Kalman filter. That means we don't keep track of the absolute angles. We keep track of the errors. And this is easier because if we use arrows for angles, we can use small angles. I will show you that in the next slide. Yeah, here it is. So this is the main reason why we use the arrow state Kalman filter. I will show you loose GNSS coupling because it's easier, but this model can easily be extended if you spend some time to a tight coupling. That means you include raw data. You use real code phase Doppler measurements from your GPS if you want to do that. The complete model that I show you here, there is a very good book by Zwiener. As I said, I had at the KIT in Karlsruhe. I attended his lectures. Very good book here. So this, if you want to see that in detail, it's unfortunately a German book, but it's very good in this regard. So I said we use arrow state, we use small angles. The good thing is we have quite for small angles, a linear relationship for everything. So we only keep track of these small angles, and we assume the total orientation here, body navigation to body, as known. And we keep track on that in a side variable in the program. So we only estimate the small errors. We avoid Euler angles, but also we avoid quaternions. We only need to use the quaternions for the integration in the strap-down algorithms. But in the Kalman filter, we don't need the quaternions. Yeah, so that's one of the most critical parts here, using the small angles. This is why the error state Kalman filter works so well compared to the total space Kalman filter. So you have these linear relationships here. It's very useful here. Okay, and that gives us the system model. So you see, this is not the prediction matrix yet. I will come to that in the next slide. This is the time derivative here. So we have our navigation state, position, velocity, the angle arrows, and we also keep track of the accelerometer bias and gyroscope bias. This is something you need to do. They change all the time. They change with every power on and so on. So this is the time derivative, and to get the system prediction matrix, there is also not this G matrix, because we need to add the noise that is introduced by the accelerometer, by the gyroscope, and also there is some noise added to the bias estimation. If we add no noise to the bias estimation, it will somehow lock in, and you say, okay, the bias then is fixed. But if you add some noise, you allow the bias to drift. So if you have a bad MEMS sensor, you increase the bias noise, so this allows the bias to randomly walk around. And this basically is the standard deviation of the accelerometer and your gyroscope, plus some tuning, and the tuning is actually important. So, what we had in the slide before, this is what I call the F matrix. And now we need to integrate that, and this is first order approximation and just multiplied by dt. And now we have the Kalman prediction matrix. So for the navigation filter, you type down the F matrix multiplied by dt, and then you have your Kalman filter prediction matrix. And we have the G matrix. Go back to this matrix here, multiplied with your sensor noises, and that's pretty much all. Kalman filter fusion, as said, simple for GNSS measurements. You take the measurements from the receiver, identity matrix here, and so you make a fusion with your GPS position and velocity. If you use raw GPS measurement, it gets a bit more complicated, but it's still doable in the same way. One thing you have to be careful in the videos, I compensate for the GPS latency roughly 80 milliseconds. It takes for the MIP blocks from measurement until you really receive the measurement. So if you introduce a 80 milliseconds old measurement, this is not so good for a small UAV that's very agile. So this is something you need to compensate for. Luckily, the MIP blocks has a time pulse, so you can measure how long does it take for the measurement to travel to your electronics, to your element filter, and say, okay, this measurement is 80 milliseconds old, and then you can correct for that. If you don't do that, the GPS will always pull back your INS by 80 milliseconds, and this will degrade your performance for a real-time control algorithm. Yeah, be careful for that. This number will probably get lower in the future, but still significant today. GPS helps you with roll, pitch, and yaw stabilization, but still, if your UAV is stable in the air, you can use the accelerometer and say, okay, the accelerometer tells me the roll and pitch angle. So you can use this equation. So this goes into your A matrix, in your design matrix. So you use accelerometer measurements to stabilize roll and pitch. You need to be careful. If you actually accelerate, you cannot use the roll and pitch from this measurement, because then it does not really point to the ground, but the acceleration. But if you have, if the accelerometer norm is close to 9.81, you can assume, okay, we're not accelerating, and the accelerometer tells me where the ground is. So we use that to stabilize roll and pitch. Heading, you can stabilize with a magnetometer. The magnetometer gives you the yaw angle, and you need to correct for the magnetic declination. Magnetometers are a bit tricky because they can be totally wrong, because someone places a metal part near it. You need to calibrate them, but magnetometers are needed to stabilize the yaw angle, unless you have a lot of trajectory dynamics. If you constantly accelerate, you can see here in this system design matrix here, north and east accelerations are correlated with the yaw angle. You can estimate the yaw angle by accelerations, but if you, for some longer period of time, you have no northeast accelerations, the yaw angle cannot be estimated by the Kalman filter, and then you need a magnetometer. And this is normally what you have in a UAV. It stays stable at one position, and you need a magnetometer to fix the yaw angle.
Do you can check exactly the magnetic anomalies? For example, we at the region of Spoelteport have anomaly about 28 degrees.
This is yeah, why you need this model. Yeah, you need absolutely. We use the World Magnetic Model 2010. Probably 2015 will come out in the next week, I hope so. This is what you need to correct for this. This is essential. For us it's 8 degrees, but still too much. So you need a magnetic model. So what I'm trying to say is, magnetometer is tricky. You need to calibrate it, you need a magnetic model, but you need it for UAVs. Otherwise, like an airplane that always makes some maneuvers might get away without a magnetometer. So now it took me 10 minutes longer. I hope you gives me that, but we started a bit later. So that concludes my talk. I know it was quite dense, but that is basically all you need to create a navigation Kalman filter, and gives you the basics to create a UAV control. So go ahead and filter your own UAV. Okay, thank you for your attention.